Thrust produced by a water rocket is equal to the product of the difference in pressure of the compressed air and the atmospheric pressure with the area of the nozzle. To achieve max flight time, we need an optimum water fraction, usually around 40% as seen on screen, as this produces a large enough impulse. Impulse is the effect of force acting over time to change the momentum of an object. If the water fraction is too small, there will be a relatively small mass, meaning a smaller impulse, causing there to be less thrust. If the water fraction is too big, then the relative mass of the rocket is also too big for significant acceleration at launch, where thrust is highest. As water leaves the nozzle, the air volume increases, decreasing the air pressure. This results in a continuous reduction of mass flow rate, decreasing the thrust of the rocket until it is zero. This is where the pressure has equalized, causing the rocket to enter its coast phase.
The directional stability of an object is the ability to be able to return to its initial equilibrium position after a disturbance, basically to control its direction. For a water rocket to be stable, the center of pressure needs to be closer to the tail end than the center of mass. The further up the fins are, the less stable the water rocket is. As you can see in the simulation, it takes a longer time for it to return to its equilibrium position. Because of this, its maximum height is also reduced. Placing fins at the tail end of a rocket moves the center of pressure closer towards the tail end and increases its stability. It therefore reaches a higher maximum height. Increasing the size of the fins increases stability, however, increases drag.
We tested the terminal velocity while the parachute diameter was changed start from 0 to 1 meter. When the parachute diameter was increased, effective area increased as well, which created more drag, so the velocity was decreased and had a longer flight time as shown.
After running all these simulations, we have decided on the cut dorsal fins as they produce less drag than rectangular fins, and hence produce a greater maximum height. We have decided to use a water fraction of 0.4 as it has proven to produce a greater flight time without increasing the mass of the rocket. We are going to use a 0.5 meter diameter for the parachute as the rocket will have a lower terminal velocity without being blown by the wind.